Welcome back, chemists. In this video, we will talk about how to draw Lewis structures. After today, you should be able to draw Lewis structures for more complex compounds, including expanded octets and polyatomic ions. Let's first talk a little bit about electronegativity. If you recall, electronegativity is the ability for an atom to attract electrons when it's chemically bonded. Electronegativity is based on effective nuclear charge, or the attraction from the nucleus to the electrons, and the distance at which those electrons are located. So it makes sense since in the case of fluorine has the ability to attract electrons so much more easily because of its very small size and the fact that the effective nuclear charge is very large. So let's talk about how to draw the perfect Lewis structure. So the steps are counting the valence electrons for all atoms, and you'll add or subtract electrons for ions. Put the atom in the middle that is least electronegative. For a single bond between the central atom and the terminal atoms, satisfy the octet for the terminal atoms, one atom at a time. Any electrons left over go around the central atom, and you want to check to make sure the central atom has a full octet, and if not, that's the only time that you form double or triple bonds. That is the step that students always struggle with, so I want to emphasize number 6, only make double and triple bonds if you have to, and notice it's the very last step, so you're only going to make those if your atoms are short an octet. So here's an example. Draw the Lewis structure for CH2O. So we'll first count up those valence electrons. So we've got 4 valence electrons for carbon. We've got 1 for each hydrogen times 2, and then plus 6 from the oxygen. So there's 12 valence electrons that we need in our Lewis structure. We're then going to put the atom in the middle that's least electronegative. Now you're going to start to notice patterns. So in my experience with drawing Lewis structures, I know that hydrogen is always going on the outside, and carbon is always going in the middle. And in terms of electronegativity, you'll definitely see that oxygen is furthest to the up and right, and so therefore that is going to be the most electronegative, so that has to go on the outside. Another thing that you'll notice with patterns is that very often the first element that is listed is going to be the element that goes in the middle. So here is the, skeletal structure that you'll see. And so we'll draw our single bonds between each of the terminal atoms. And then we have right now 6 electrons in our picture. So we want to satisfy the octets of the terminal atoms now. Now hydrogen's already satisfied with 2 electrons each. So that means we have to look to the oxygen. So we've got 6 electrons in our picture because each line represents 2 electrons. And this will be 8, 10, and then 12. And I ran out of electrons. Any electrons left over go over the central atom. We don't have any. And then this is where this important step comes in. Again, check to make sure the central atom has a full octet. So if you notice, carbon only has 3 lines to it, indicating 6 electrons around it. So guess what? We have to remove the electron pair from the oxygen to make a double bond. So we're going to wipe one off and make that double bond. Let's do the same thing for HCN. Again, notice we're going to count up those valence electrons. Put the atom in the middle that's least electronegative. It's already discussed, right? N is up and furthest to the right, so that's definitely going on the outside. Carbon's always going in the middle. So we'll put the C in the middle, the H in the end around it. Draw our single bonds to each of those terminal atoms, and then satisfy the octets of the terminal atoms using the remaining electrons. So right now we have 4 electrons in our picture. This is going to be 5, 6, 7, 8, 9, 10, and we ran out of electrons. We have no remaining electrons to go around the central atom. And again, if you're looking at this, you can see right away that carbon is not satisfied. So I'm going to have to take not 1, but 2 pairs of electrons off that nitrogen to make that triple bond. Let's try drawing one for a polyatomic ion. So we've got the nitrate ion here. So again, we're going to count up those valence electrons, but this is a little different because besides factoring in the atoms and those valence electrons, notice that I added an electron, and that's important because that's what that -1 charge means on the nitrate ion. So you want to make sure that you add that extra electron. Again, we'll put the atom in the middle that's least electronegative. In this case, nitrogen's definitely going in the middle because we have a lot of oxygens there. And then we're going to position those oxygens around it. We'll form our single bonds just like usual. And then satisfy the octets of the terminal atoms one at a time. I'm just going to count. Right now we have 6 electrons in our Lewis structure. So this is going to be 8, 10, 12, 14, 16, 18, 20, 22, and 24. And I ran out of electrons. We don't have any remaining electrons. And so now again, step 6 here, we have to check the octets. Each oxygen has 8, but look at the nitrogen. It only has 6. So that means that you can take an electron pair from any of those oxygens and make a double bond. And there we go. Now, because this is an ion, the other thing that we have to do is we have to show that it's an ion. So what we do is we put square brackets around it, and then we add the charge. And so that is going to be the Lewis structure for nitrate. Let's talk about expanded octets. So an expanded octet occurs when there are more than 8 electrons in the valence shell of an atom. And you may say, how can this happen? Well, this occurs in elements in the 3rd period and beyond. And the reason why we more than likely see that is because, remember, in the 3rd energy level, we have the S, the P, and the D. And so we theorize at this point that the reason why we can see these expanded octets is because we use those empty d orbitals to occupy those to put those electrons in. And so these we'll expect to see these expanded valence shells whenever you have a larger central atom, again in the 3rd period or below, and they're bonded to a very small electronegative atom such as fluorine, chlorine, and oxygen. Now, in general, when you're drawing Lewis structures, when choosing between Lewis structures, you want to choose one that's going to satisfy the octet rule if possible. And so you'll know that just as long as you follow the procedure that has been given to you. So here's an example of an expanded octet, SF6. So we'll count all the valence electrons, right? So we've got 6 from the sulfur, 7 from each fluorine times 6. So that's 42. And then that's 48, okay? And then we're going to put the atom in the middle that's least electronegative. So we've got sulfur in the middle, each fluorine around it, draw single bonds, and we're going to satisfy the octets of all the terminal atoms. So right now we've got 2, 4, 6, 8, 10, 12 electrons in our picture. And so right now we're going to go, that's 12, so this will be 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. Perfect. Any remaining electrons go around the central atom. We've hit 48, so we've got our max, so there are no remaining electrons. And the last part is to make sure all the octets are satisfied. Now, obviously, sulfur is an expanded octet, so definitely has an octet of electrons. It's got an expanded octet, and each fluorine has 8 as well. Here's the Lewis structure for XEF4. Well, again, we'll count up those valence electrons. We have 36. Put the atom in the middle that's least electronegative. In this case, it's going to be xenon, which you're probably weirded out by because we always say that the noble gases don't react. Well, there are some cases, like in this case, fluorine is just so electronegative, it has such a desire for those electrons, and those valence electrons in xenon are so far away from the nucleus, they're going to be sharing those electrons whether they like it or not. We'll draw our single bonds, and right now I have 8 in our picture. So if that's 8, we're going to satisfy the octets of the terminal atoms. That'll be 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I count 32 right now. Notice we have 32 of the 36. So this is where your remaining electrons are going to go around the central atom. So this will be 34 and 36. Finally, we want to check to make sure that there's an octet for everything, and there absolutely is. Notice I'm not making any double or triple bonds because I don't need to. Everything has an octet. So now I'm going to ask you to go back to your bell work, where I ask you to intuitively or try to draw those molecules and correct your mistakes given this new set of rules. And then you can turn it in. I'm going to ask you to please start worksheet 3H for homework. Thank you so much for watching.